So we're going to take the derivative of f because we're going to look for critical points. And critical points is when it doesn't exist, the derivative doesn't exist, or the derivative equals to 0. So it's 2 over 7 x to negative 5 over 7. Okay, because 7 over 7, if I minus it, becomes 5 over 7. Okay, and the chain rule would be multiplied by 1, and we don't need that. Now this problem is 2 over 7, the 7th root of x to the 5th power, which is ugly. But one thing we know, this graph will never become 0. Okay, and if it becomes 0, look, if I plug in 0, it's undefined. Oh, that doesn't make sense. If I plug in, if x will never equal to 0, this answer will never become 0. So we have no stationary points. But then, does this graph not exist? If x was 0, we would be dividing by 0. So at x equals to 0, this is a critical point. Does 0 exist in the regular graph? 0 to the 2 over 7 power? Yeah, that's 0. So it does exist in the regular graph. It just doesn't, the derivative itself doesn't exist. So we see that's a critical point. So I'm going to draw a sign chart here. And my only critical point is when x is 0, and this is undefined. Now, my follow-up question is, what does the slope look like on the left and right side of this? What does the slope look like on the left and right side of it? So I also included my boundaries at -5 and 3. So on the right side, if I plug in a positive 1, 2, 3, 4, 5, this would stay positive. And if I plug in a negative number like -1, this would become negative. Because 2 over 7, the 7th root of -1 to the 5th power, would still be -2 over 7. It would still be a negative number. So we're assuming it will always be negative. Now, why do I know it's always going to be negative? Here is a brief illustration. Here is my number 1 and to my number 5. Let's say these are my only zeros to the graph. I've told you, I promised you, these are the only zeros to the graph. So if I go down here, can I sneak up before I get to 5? If this is continuous, no, because we told you there are no zeros, there are no borders to get out. You can't, it's not like a dolphin jumping out of the water. You're stuck to the next 0. So if you're negative, you stay negative all the way to the next 0. If you're positive, right, you stay positive all the way to the next 0. So what happens is, I know at 0, this is undefined. We check on the right side, you're positive. That means you're going to be positive all the way. If you're negative, you're going to stay negative all the way. You're stuck on the sign to our next critical point. Okay, so let me ask you this now. From a negative to positive, does that look like a minimum or maximum?
Minimum.
It looks like a minimum, right? Yeah. Now, here is something else cool. I can tell you the endpoints are mins or max. I can tell you without even plugging in a number. Without even plugging in a number, I can tell you that's a min or max. Look at the slope. If we start at the endpoint and we have a negative slope, aren't we coming down? So would that left endpoint be a max or a min?
A max?
A max. Because you start at a high point and you start losing money. If your slope is negative, that means you're sliding down. That means you started from a high point. You don't start the slide at the bottom, right? So we slide down from the top. So we see this is a max at least. Whether it's an absolute or local, we don't know. Well, for sure it's a local. We don't know if it's absolute. On the right side, the slope is climbing up to that right point. See, the slope is positive. So would the right side be a max or min, the right endpoint?
A max.
A max, I'll take that. So we actually only have 3 points to compare. We have f at -5. What's the y value here, right? What's the y value? What is the f at 0? And what is the f at 3? We only have to compare 3 points, and we're looking for the actual y value. We use the derivative to find out what's special. Is it going to be a max or min? But then we have to then compare. So at negative 5, so this is our original function up here is negative 5 to the 2 over 7, which is squaring gets rid of the negative sign. So it's 5, 2 over 7. 5 to the 2 7th power. Okay, if I plug in 0, 0 to the 2 7th power is still 0. Okay, so far we know 5 to the 2 7th is bigger than 0. All right, I'll take that. And 3 to the 2 7ths. 3 to the 2 7ths. Now, what do you think is going to be bigger? I don't know. 5 to the 2 7ths or 2 to the 2, oh, sorry, 3 to the 2 7ths? I'm going to plug this to my calculator just to double check. Where are you, cell phone? So 5 to the exponent 2 over 7 is 1.58. 3 to the exponent 2 over 7 is 1.36. And they are close, but our absolute maximum is 1.58 at x equals to negative 5. Okay. How about what's the absolute minimum for this problem? Well, we said there's only one minimum value, right? We were able to tell that by the slopes at 0.
That says 1.36, right?
1.36, yeah, when I plug it into my calculator.
Mr. Ko, how did you get the negative 5 and 3?
How to get the negative 5 from the 3? These were the initial boundaries for the problem, the left and right bound. So you check the interior, and then you check the endpoints, because you don't know. Maybe you're on a high castle. The right and left wall are super tall. I don't know.
Wait, Mr. Combe. So
Yes.
the critical points or whatever make the 0 equal to 0, x equal to 0, right?
Or not exist. And in this case, we couldn't divide by 0. That's why 0 was another critical point.
Mm-hmm.
So 0 is our only critical point?
Yes, because
Right.
I couldn't make the whole function equal 0, right? 2 divided by 7 will never become 0.
Mm-hmm.
Okay, let me go ahead and graph this. This was x to the 2 7th power, x to the exponent. Here it is. And then parentheses 2 over 7. Okay, if you notice here, I don't really change our graphs to 1. Okay, we said our graph is from negative 5 to 3. Let's go squeeze that in there. So here's negative 5. We said was 1.5 something. We said 3 on the right was 1.3 something. And 0 is our minimum. So looking at this graph, of course, looking at the graph, you can tell the left negative 5 would be the maximum. And the right would be a local max. And the minimum would be at 0. But we were able to tell all about this function without having to graph it. Were we correct in our assumption that the slope was negative on the left side and positive on the right?
Yep.
We were, right? And we didn't have to graph this nice graph. We just had to do my stupid sign chart. Okay. And with a couple of things that we noticed, like on the left endpoint, if the slope is negative, that means we left a high value. That was a max. And on the right side, the slope was positive right before we hit the wall. That means we were climbing up to it. That's another max. But we didn't know which max was the absolute max. That's how we had to plug them in to figure out which one was the absolute max.
On a test, would we have to do like a ton of these problems really quick, or we would have time?
No, you would be timed so that you would have enough time. Like you have to do them quick because the first step was I didn't even think about it. I just did the derivative, right? And then you have to draw. You decide what's my maximum, what's my minimum using the signs. Negative to positive is a minimum, and then we would check the endpoints. This last part, checking the endpoints, and then comparing all three values. Now let me give you this thing. On the AP exam, if they ask you for the absolute maximum, you must check the critical points as well as the endpoints. You have to write them out so they see that you compared them. You can't just say, oh, it looked big. Oh, I had a feeling. You actually have to show, hey, 1.8 is bigger than any of these other values. That's why you, sir, are an absolute maximum.
Mr. Koch,
Yes.
how did the -5 to the power of 2 divided by 7 become positive again?
When you square something,
Yeah.
what does it do to the negative sign?
Oh, it makes it.
Yeah.
Yeah.
So that's the reason why. And it's something you don't have to do that. I just did that. Because some people have been, oh, Mr. Code, negative, that's the lowest number. Right, let's do one more. And let's see, is this next problem any different than what we just did? Any different? Y is equal to 2x squared minus 4x plus 9. Okay, so y prime. So, okay, also find the extreme values of the function and where they occur. Okay, looking for extreme values. So minimums, maximums, 2x, sorry, whoops, 4x, take the derivative 4x minus 4 equals 0. First step, what are my zeros? 0 at x equals to 1, right? Plus, wait, whoop, plus 4 plus 4, 4x equals to 4 divided by 4 divided by 4, x equals to 1. This is my only 0. So at x equals to 1, this is my only 0. And my derivative is 0 here. So this is my sign chart. And this only deals with slopes, okay? This is all our slopes. The slope is 0 when x is 1. So what's the slope on the right side of 1? What's the slope on the left side of 1? So pick a number bigger than 1, 2, 3, 4, 5. That would make this positive on the right side. 0, negative 1, negative 2 on the left side here. If I plug it in, this would be negative. So can you guys tell me, like don't answer right away, but think about it. The slope goes from negative, 0, positive. Would it be a max or minimum at 1?
Minimum.
Okay, minimum, right?
Minimum.
Are you guys all cool with me drawing this like dumb, like line, line, line?
Looks
I
like
think
a
it's
smiley
helpful.
face.
Yep,
That's what I was about to say.
looks like a joker. If not, remember, use your hand. Negative, 0, positive. That's a bowl, right? And the middle point of that bowl is going to be a minimum value.
And how did you find the left and right if they are negative and positive?
Okay, remember, these are slopes, right? So which equation, Maxim, is a slope? Is it 2x squared or 4x? Which of these equations is a slope?
First 2x squared, I think.
The slope.
4x?
The slope of the graph. This is my actual graph.
Oh, okay.
Y prime is my slope. Okay?
Yeah.
So to find slope, that's y prime. So I plugged the values here into this problem here. And that came out to be a positive value. So it's a positive slope.
Oh, okay.
So you can pick any number you want, right? Pick 0 here. Please, please pick 0 if you can pick 0. If I plug in 0, that's going to be negative. And that'll be negative for the rest of its life. Poor guy. Pick easy values for yourself. Now, here's something I want to show you that's kind of cool. If I rewrote this as x minus 1, you can see the tipping point is at 1, right? And if x is bigger than 1, that would be a positive. But if x was negative, like less than 1, this would be negative. You can automatically tell that from Algebra 1. Okay, so the question says, choose the correct answer below, fill in the answer box to complete your answer. So does this graph have an absolute maximum? Is this graph bounded at all?
No.
No.
No, so doesn't this graph just keep going forever? So there
Yeah.
is no absolute maximum. You could try to tell me it's infinity, but it's not, because what about infinity plus 1? What's infinity plus 2? Well, that's infinity, right? But you can't beat my infinity. So infinity is an answer for us when it comes to absolute maximum. We have to cap it off to get a maximum value, absolute maximum value. Do we have an absolute minimum, though, for this graph?
Yeah.
We do, right? And our absolute minimum is when x equals to 1. No. Our minimum value is we don't know yet. We know it happens at x equals to 1, but what is the minimum value? We got to plug it in to figure out what that minimum value is. 2 minus 4 plus 9.
We plug it in on the initial equation.
Right, because that's the actual positions, actual points of the graph.
Mhm.
Okay.
Wait, Mr. Ko, quick question.
Yeah.
Why, when this slope or this graph or the derivative of this graph is positive, so why is there a negative side? I'm sure that was answered before, but I'm so
Wait,
confused.
I'm sorry.
Like the left side. Why is there a left side?
Right here?
Yeah.
Okay, so think of this as a teeter-totter, right? Okay, so we know it's balanced at 0, but what's going on here and here? We don't know. So we pick values. We said those x was 1. So if I pick 2, 3, and 4, what does 4x minus 4 look like on this side? It looks like it'll be positive. But 4x minus 4 for 0, -1, -2 would be negative.
Okay, so the graph wouldn't go below 0, or the
I don't know
right.
anything about the graph. This graph here,
Oh.
okay, sorry, the graph I drew here is not a real graph. It's just a trending graph. The graph goes down, 0 up. I don't really know where the position of this graph is. All I know is that x equals to 1. The graph could look like this, this, I don't know. Something along that line.
I think it's just because I'm used to when I see an equation like that, I'm used to just a straight line going one way, not both ways. But
And what happens, remember, this is not a line equation. This is us talking about the slopes. If the slopes will be positive or negative.
oh, so these are just the slopes
Right.
of
See,
the
that's the
other one.
slopes of the graph.
Oh, okay.
And
That
it's
makes
referring
sense.
to what's the trend in the parabola. The parabola is trending downward before 1. And the parabola is trending upward after 1. And that's what the slope gives us, the trend of it. Great question. I was asked, does it matter for intervals if they write parentheses or brackets? And it does. Parentheses means don't include it. Brackets means include it. Oops. So let's say a dumb parabola. If I pick a parabola from 0 to 1, if I say don't include it, that means these are empty. If I say include it, these are solid. Now, this has implications for maxes and minimums. If this was my graph and this was the parentheses, that means I have no max and no min. They wouldn't do that to you. They wouldn't do that to you. But why wouldn't we? What would the max be? Even if I call this 1 here and this is 0, what would the max be? Is 1 even included? Nope, it's not. So are you going to tell me 0.99? How about 0.999999999? I can add another 9 and be bigger than yours. So it would actually be no max and no min because they're undefined. Well, the max here would be 1 and the min would be 0. Okay, great question. All right. Darn it. This time that we have. Okay. We are out of time. We burned out all the time. Wait, no. Do we? Do we have time? No, we don't have time left. Gosh, I want to give you guys homework. I wanted to go over this new
It's
lesson.
fine. We got homework from last time.
Yeah, Mr. Code.
Oh,
Yo.
shoot. Ah,
Mr. Ko, didn't you post like a new homework?
I did.
Are you gonna have to delay that now?
I'm gonna have to delay it unless if I make another video off the side to talk about this homework.
No.
I think it's okay. I think we need to learn hands-on in class.
Yeah.
We won't be able to ask questions, you know? Yeah.
You guys are oh my gosh. All right. Okay. Well, I'll give you 1 day break today. Okay, 1 day break, and then we'll catch up to this on Thursday. Okay. So ignore the homework 24, but it is a cool theorem. I swear it is a cool theorem. But you guys hopefully are working through these. If you guys went back and you got 100, because you graphed it, go back and redo it again. That's all I can say, right? Do you know, will it let you go back and redo the problems after you finish?
Yeah, but you have to like go. You can just click like show similar problem.
Okay,
Yeah,
great.
like a similar question.
Perfect. So everyone, if you guys did use a graph, go back and try doing this without a graph. If you want a graph on the side just to support yourself, that's okay. But you have to do this all without graphing. Okay, and that's the whole point of this. All right. All right, we're done. Thank you.
Thank
See
you,
guys.
Mr. Ko.
Sorry.
Mr. Ko.
Oh my
Have a
gosh.
good one.
Bye.
Thank you, Mr.
Bye.
Ko.
Go.
Thank you.
Thank you.